Hello everybody. In this lecture we will be solving 1999 IMO problem number 3. Here is a view of this combo problem. Consider an n by n board where n is a fixed even positive integer. The board is divided into n square unit squares, and we say that two different squares on the board are adjacent if they have a common side. For instance, this and this, they are adjacent because they share a common side. However, this one and this one, they are not adjacent because they are only sharing a vertex but not a side. Okay, then n unit squares on the board are marked in such a way that every square on the board is adjacent to at least one marked square. We would like to find the smallest possible value of n. So to begin with, what I will do is I will make the following. I will write n as follows. I realize okay, so the first thing that I do is I color my square board, my n by n square board, where n is equal to 2k. Remember, n is an even integer, like a chessboard. Okay, so I covered it, and in this particular example, I have a 10 by 10 chessboard. So n is therefore equal to, I claim, n sub b plus n sub w. And what I mean by n sub b and n sub w is n sub b is the minimum number of black squares that must be marked so that the condition of the problem is satisfied, that every every white square on the board is covered, right? It has a neighbor, an adjacent side to a marked point and a marked square. And similarly, NW is the minimum number of white squares that must be marked so that, again, the conditions of the problem is satisfied. Do you agree with me that these two numbers, they have to be added, right? So they do not have anything in common. So you cannot overcount, right? So I'm not overcounting by adding these two numbers, right? Because there is no way that a black square, so a black square here will be covered if one of these four is marked. There's no other way. By marking this black square, I'm not covering this black square. So that's a crucial observation. Now let's try to answer. For instance, let me try to count NW. By symmetry, I will later on claim that NW and NB are basically equal to each other, right? For instance, the simplest way to observe that would be just to rotate the chessboard by 90 degrees, actually. Okay, so going back to our claim, let's start. Consider the following coloring, marking, I should say, rather. So let me go ahead and mark this, and then skip this. So what I'm doing is, okay. So let me do my work, and then you guys try to see what I'm doing here. Okay, so I hope I'm not too mysterious here, but do you see this marking? Okay, so what did I do here? So first of all, I paid attention to the diagonals, to the lines parallel to the diagonals, like this. Okay, so like this diagonal, this white diagonal. I'm focusing on the white diagonal. I need a marking of the whites so that the blacks are adjacent to one of these marked stuff, right? So yeah, oh, sorry for that, I skipped this one. Okay, good. So first of all, do you guys agree that all the black squares here have been are now adjacent to at least one marked white. Let's make sure we understand this. This black is adjacent to this one. This black is again adjacent to this mark. This, for instance, this one is adjacent to this guy. This one is adjacent to this guy, to the same guy. This guy is to the same. So therefore, every single one of these black squares have an adjacent edge or a common edge with a marked white square. So now let me count how many marks that I did put on this chessboard. What I will do is consider this main diagonal. Okay, so with respect to this main diagonal, I started by putting one mark here, +1, and then I skipped one diagonal, and I went to the next one, and I did put 3 more, and then I skipped one diagonal here, namely this one, and then I went to the next diagonal, and this time I put 5. Where did I stop? Well, you keep putting the marks until what? Until you reach let's call it plus k1, where k1 is the greatest odd integer not exceeding k, right? So this guy is greatest odd integer. Obviously it is odd because my series is odd integer not exceeding k. In our particular example, I have a 10 by 10 board where n is equal to 10 and k is equal to 5. Remember how I defined k. So, and obviously I stopped at 5. But then I continue. I'm not done yet. So I still have the top left right corner. So I add, actually in this case, once I reach the diagonal, let me go back to that vertex and let me go this way, count this way. So I added 2 more here. Then I added 4 more, and so on. So where do I stop? Let's say I stop at k2, I stop at k2, where k2 is in fact the greatest even integer this time, greatest even integer not exceeding k again. Do you see? So +2, +4, all the way to plus k2. But now nw therefore is simply equal to 1 plus 3 plus plus k1 plus 2 plus 4 plus plus k2. But it is obvious that k1 and k2, the way that they are defined is such that what I'm doing is, if I rearrange this sum, I will get 1 plus 2 plus 3 and so on. Eventually one of these numbers will be equal to k, right? Because so therefore, because here k1 is less than or equal to k, here k2 is less than or equal to k, such that they are the greatest. So there are plus all the way up to k, which is just k times k plus 1 over 2. So therefore, this marking here, let's call the set of these marks as the set S. In our set S, okay, so that's all right, so that's not NW yet. I don't know if this is NW, sorry for that. So this is the number of elements in my set S. So this is the set of markings, marked cells. So this set has k times k plus 1 over 2 elements in it. Now in the next step, I want to show that, yes, I want to show that S, show claim. I claim that S is actually equal to n, in this case, because I marked the white ones, is equal to NW. That's what I need to show. Proof. So first I claim that NW cannot be less than S, which is this sum here, K. And the reason is simple, because the way that I marked here is efficient. Well, what I mean by efficient, I mean that no black square is adjacent to 2 different white squares. Every black square is only adjacent to a single white square. So therefore this marking here is efficient. So NW, whatever it is, cannot be less than this number. So this is the lower bound for NW. And secondly, I also claim that NW is less than or equal to S as well. What I mean here is, I mean that S is a successful set, is a successful marking, right? Do you agree that there is no black square which is outside the condition of the problem? The condition is satisfied by this marking. So this marking cannot have, by definition, because definition NW was the smallest by its definition, so therefore because our set S satisfies the condition, it has to be greater than or equal to NW. Combining these two, the claim is established that S is actually equal to NW. Now let's go back and now prove the following claim. I now claim that NW, which is equal to S, is also equal to NB. So why is NS, NW, and NB equal to each other? Well, this one is also obvious, because all I do is consider the following marking. Now, instead of the main diagonal like this, let's consider, which color should I use? Okay, so maybe this one. Consider this white diagonal now. If I now do the marking as follows, I mark this black one, skip this, and then mark these, skip the next one, mark these. Do you see what I'm doing? I'm just rotated the thing, and then I'm just doing the same marking business. I'm doing nothing different. Boom. And again, on the top left corner, you are adding +1, +3, +5, and so on. And on the bottom right, we're adding +2, +4, and so on. So therefore, this is no different than NW. So NB is equal to NW, and so these are all equal to K times K plus 1 over 2. Finally, so we can conclude that N, which is equal to NB plus NW, is simply equal to 2 times K plus 1 over 2, or K times K plus 1. But recall that K was simply equal to N over 2 early on. We started with that because it was given in the problem that N is a fixed integer. So finally, this would imply that N is simply equal to N over 2 times N over 2 plus 1 is the final answer. And this is the minimum value, the minimum number of squares that must be marked such that all the squares inside our grid, the n by n grid, is has a neighbor, has a square adjacent, has an adjacent marked square. Okay. Okay, but that's all. So hope you enjoyed the video, and looking forward to see you guys in our next lecture.